Hi, thanks for joining me. Today I'm going to be going over problem 1 from week 1 of the Summer Invariants Puzzle Competition from 2022. If you don't know what this is a puzzle competition being run by the Maths Society at Oxford. Every week over summer they're going to be releasing 3 different problems, and the person who answers the most correctly at the end will win a prize. Anyway, I'll leave a link in the description below to the Facebook page of the Invariants where you can find out more information. Anyway, this is the problem we have today. We have f of m being equal to the largest prime factor of n, and we have a sequence of numbers an, where the first term a1 is 2, and then to find subsequent terms we have an plus 1 equals an plus f of an. So to work out the next term in the sequence, you take the previous one and then add on f of that term. We want to find the largest k such that ak is less than 10 to the power of 4, so less than 10,000. Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so the first thing I want to notice is that an is very clearly an increasing sequence of positive integers. To get from one term to the next, an plus 1 is equal to an, so the previous term, plus f of an. And remember, f of an is just the largest prime divisor of an. So in particular, it's going to be a prime number, so at least 2. So each time we're going to be jumping up by at least 2. So going from one to the next. So the question certainly is well defined. What's the largest k such that ak is less than 10,000? Because at one point the ans are going to pass 10,000, and because it's an increasing sequence, it's never going to drop down beneath it again. So certainly the question is well defined. Anyway, what I want to do is go through quite a nice observation which we're going to use to help solve the problem. So suppose there exists k such that the kth term in the sequence ak is equal to pi times pi plus 1. So pi here is just the ith prime number. So suppose we look at our sequence of numbers and there's one number which is the product of 2 consecutive primes, pi times pi plus 1. Well, then what we want to do is kind of have a play about and see if we can find out some more information about the subsequent terms in the sequence. Anyway, suppose we have a term, a k such that ak equals pi times pi plus 1. Well then, notice that for all positive integers L, with L strictly less than pi plus 2, so the I plus 2 prime, we have the f of L times pi plus 1 is going to be equal to pi plus 1. So in other words, whenever we do f of L times pi plus 1, we're going to get pi plus 1 out, where L is a positive integer less than pi plus 2. Hopefully that's quite clear to see because, well, this guy here clearly has a factor of pi plus 1, so f of it is going to be at least pi plus 1. Its biggest prime factor is going to be at least pi plus 1. But it's clearly not going to have any prime divisors bigger than or equal to pi plus 2, because otherwise L would have to be bigger than pi plus 2, which is not the case. So f of L times pi plus 1 equals pi plus 1. Well, how can we use this to work out, or to look at subsequent terms in this sequence? Well, what is ak plus 1? Ak plus 1 is just going to be ak plus f of ak, so pi times pi plus 1 plus f of pi times pi plus 1. But using our little observation here, a little thing that we've written up here, with L equals pi, it's certainly less than pi plus 2, so f of it is just going to be equal to pi plus 1. So all in all, we're going to get pi plus 1 times pi plus 1, like so. So that's ak plus 1. What about ak plus 2? ak plus 2 is equal to ak plus 1 plus f of ak plus 1, so pi plus 1 times pi plus 1 plus f of pi plus 1 times pi plus 1. And again, this thing here, we can use our little thing that we've written up here with L equals pi plus 1, which is certainly less than pi plus 2, and get that this thing here, f of it, is going to be equal to pi plus 1. So all in all, this guy here is equal to pi plus 2 times pi plus 1. And hopefully you can see the pattern. We've got a 1 there, we've got 2 there, and the next line we'd have a 3, and this pattern continues. It doesn't continue indefinitely because this L here has to be less than pi plus 2, and you can just check for yourself that you can continue this up to ak plus pi plus 2 minus pi. So whatever that number is there, this thing here is going to equal pi plus 2 minus pi times pi plus 1, like so. So the k plus pi plus 2 minus pi term is going to be equal to this guy here, but what's quite nice about this is we've got a plus pi and a minus pi. They're going to cancel, so this guy is going to cancel with this guy, and this thing here is going to equal just pi plus 1 times pi plus 2. So we have that if we have a term which is the product of two consecutive primes, if we go down a few more terms in the sequence, we're going to get the product of the next two primes. So we've got pi times pi plus 1, and then this guy here is pi plus 1 times pi plus 2. And we can kind of actually know how many steps to continue down our sequence until we get to this guy here. So that's a little observation I wanted to make. If we have the product of two primes as a term in our sequence, then the product of the next kind of pair of primes is going to be in our sequence as well. And then kind of by induction, we're going to get all products of those pairs of primes beyond that point, if that makes sense. Anyway, I'm going to clear up the whiteboard and then we'll continue. Okay, so I've written up what we just proved there. If ak is equal to pi times pi plus 1, then ak plus pi plus 2 minus pi is equal to pi plus 1 times pi plus 2. Now, this would be pretty useless if there were no terms in the sequence which were the product of two primes, but thankfully there's a very small term in the sequence which is the product of two primes. So remember, we have a1 is equal to 2, so that tells us that a2 is going to be equal to 2 plus f of 2, which is of course going to be 2, so that's 2 plus 2, which is 4, and then a3 is going to be 4 plus f of 4. What's the largest prime factor of 4? 2, so we've got 4 plus 2, which is equal to 6, and that of course is 2 times 3, which is p1 times p2, like so. So in this case, we've got k is equal to 3, because we've got the subscript 3 there, and our I is just going to be equal to 1. We've got the product p1 times p2, so pi times pi plus 1, like so. So quite nice, we've got just a small term in the sequence, which is the product of two consecutive primes. Now we can just go ahead and use this result here. So we have the a of 3 plus, now remember I is 1, so we've got pi plus 2, so the third prime, minus p1 is going to be equal to p2 times p3. But we can actually continue this one step further. If we call this new number 3 plus p3 minus p1, if we call that, say, k prime, we can just use our result again, this guy here. So then we're going to get the a of k, which is now 3 plus p3 minus p1, plus p4 minus p2. This guy here is going to be equal to p3 times p4. So the product of the next pair of primes. And then we can kind of continue this inductively to get the a of 3 plus p3 minus p1, and this is all in the subscript, hopefully that's clear, plus p4 minus p2, plus so on all the way up to pn minus 2. This guy here, the square brackets is just to denote that it's in the subscript. This thing here is going to be equal to pn minus 1 times pn, and this holds for arbitrary n. And we can just check that that's true in these two cases. When n here is 3, we get 3 and then 1, which is what we have here, 3 and 1. And when n is 4, we get 4, 3, and here we get the n is 4, p4 minus p2, like so. So this is the kind of general formula, and it works for arbitrary n. But obviously, this guy here in the subscript, it's a nice long infinite series, but thankfully it is telescoping. Most of the middle terms are going to cancel with one another. If I just put the next term here, which would be p5 minus p3, this p3, this p minus p3 is going to cancel with this p3. The next term would be p6 minus p4, the minus p4 would cancel with this p4, and so on. So in fact, most of the middle terms will cancel, and what we'll be left with is just a few terms which we can just go ahead and evaluate. Anyway, I've run out of room. Let me clean up the whiteboard, and we'll continue. Okay, so we have a of this guy here is equal to pn minus 1 times pn. Let's cancel down the middle terms. Well, what are we going to be left with? p3 we said is going to cancel with the next term here, the minus p3. So we're going to take the first two negative terms here, so the minus p1 and minus p2, and take the last two positive terms in our telescoping series. If you need to, go ahead and just write this out, perhaps write out a few more terms if you don't see the cancellation already. But this is just going to be equal to a of 3 minus p1 minus p2 plus pn minus 1 plus pn, like so. And that's going to be equal to pn minus 1 times pn, like so. But we know what p1 and p2 are. It's the first two primes, 2 and 3. So we've got 3 minus 2 minus 3, so that's just going to give us minus 2. If I get rid of this and replace it with minus 2. So a of minus 2 plus pn minus 1 plus pn is equal to pn minus 1 times pn. And that is like a general formula that we can help to use us. Now, it's easy to check that 97 and 101 are consecutive primes. They're both prime numbers, and the only potential prime in between would be the odd number 99, as clearly divisible by 9. So 97 and 101, they're both primes, consecutive primes, so we can just plug them into this formula here, and we're going to get A of minus 2 plus 97 plus 101 is equal to 97 times 101, which is 9797, but I'm also just going to keep it as 97 times 101 for now as well. Minus 2 plus 97 plus 101, that's 198 minus 2, 196. So A of 196 is equal to 9797, which you can see is just under 10,000. So we know that the final answer, K, is going to be maybe 196, maybe just a small amount more than 196, but not too much bigger. So A of 196 is 9797. So what we want to do is see if the next term, A197, is that bigger than 10,000 or less than 10,000. Let's just go ahead and work it out. A of 197, just using the definition of A, is going to be equal to A of 196, so 9797, plus F of 9797. But F of 9797 is the largest prime divisor of 9797, and it's clearly just the product of two primes, and the bigger of which is 101. So we've got 9797 plus 101, and you can check that this is just 9898, which is nice. It's still under 10,000, so we know the answer is at least 197, but not going to be too much bigger. But 9898, I'll just write for now, is clearly 98 times 101 as well, and 101 is still a prime number, it hasn't changed. What's the next term in the sequence, A198? Does this go beyond 10,000, or does this remain under? Well, let's just use the definition again. It's going to be equal to the previous term, 9898, plus F, plus F of 9898, which is just 98 times, or F of 98 times 101. What's the biggest prime divisor of that guy? It's clearly 101. 98 isn't prime, but we don't even need to worry about the prime divisors of 98. They're clearly going to be less than 98, and thus less than 101. So we've got 9898 plus 101, and this guy here is 9999, and that is the biggest number, less than 10 to the 4. So we don't need to compute A of 199, because we know that that's going to go over 10,000. So we know what the final answer is. It's 198. The final term, or the smallest k, or the largest k for which AK is less than 10,000, is k equals 198. Anyway, I hope that solution has made sense, and I hope you have enjoyed this problem. I'll be making solution videos for the other problems as well, so if you're interested, do stick around, and if you're new to the channel, please do consider subscribing as well. If you made it this far into the video, hopefully it means you enjoyed it and enjoyed my explanation. So if you aren't subscribed, please do consider subscribing, and yeah, catch you in the next one. Have a great day.